This is the Unit 15 review. So this is another one of those reviews where through the concepts I have, pretty extended paragraphs describing sort of my ideal answers to some of these questions. You don't have to copy everything down, of course. Just put it in your own words. Try and remember, the big ideas and things like that. So I'll let you kind of read through a lot of that, but I'll explain the finer points here. So these first two questions are about equilibrium, and the biggest thing that you have to understand about equilibrium is that it has to do with balance. And so you've got a system that you're looking at and some property of that system, and there are processes involved, but whatever the processes are, they're sort of canceling out in such a way that you get stability or balance over time. That's the idea of equilibrium. So in class, I went through some different analogies with that. You can watch the equilibrium note set if you want some more in-depth explanation of that, but equilibrium is about balance in some property over time, due to two opposing processes happening at the same rate. So in chemistry, specifically what we're talking about is how much of the product and how much of the reactant there are, when a reactant sort of stops having a net change. And you can see here in question number 2 that for chemistry, that's happening when the rate of the forward reaction and the rate of the reverse reaction are equal to one another. So looking down here, one of the things it says, equilibrium doesn't mean that there are equal amounts of something. For instance, you don't have to have equal amounts of reactants as you do products. Some reactions are heavily product favored or heavily reactant favored, and so there's not necessarily equal amounts. That's not what equilibrium means. It also talks about what's required here for equilibrium to be happening. Some different things. Closed system helps because that means that, say if you're looking at water being in equilibrium, if you have a closed system and the water can't get out, it's just going to be cycling through, which means that there has to be some sort of balance there. You can have an open system and still have equilibrium. In that case, what would be happening is, there's something coming in and something going out, and what's coming in is going out at the same rate. And so an example of an open system which would have equilibrium, I kind of use the example of a population of a city, for instance. If it was at equilibrium, what would happen is there'd be people moving in and there'd be people moving out, or there'd be people being born and people dying, and that would all be happening at the same rate. So the general population wouldn't change at all. It's not a closed system, but it is at equilibrium. So what has to happen here is you've got these two processes, but the rates are the same for the processes, and so it ends up balancing out overall. All right, so that's it for the first two questions. Hopefully you kind of understand the concepts of equilibrium and how it relates to chemistry. Question 3 here is talking about the idea of dynamic equilibrium. So dynamic means that something is moving or changing or something like that. Dynamic means, it's kind of flexible over time. And so what's happening here with dynamic equilibrium is that it's emphasizing that when equilibrium is reached, things don't just all come to a halt. Okay, chemical reactions are still happening even when the system is at equilibrium. So you get the forward reaction happening and the reverse reaction happening. It's just that they're happening at the same rate. I'll talk a little bit here in the next question about the collision theory of chemical reactions, but what's happening here is that there are still atoms hitting each other. They're still going into that transition state. They're still creating products or reactants, and as I said, things are still happening. It's still, action is going on. The opposite of that is sort of called static equilibrium. Static equilibrium is something that we talk about sort of in physics. And what happens there is that when equilibrium is reached, everything sort of stops moving. Everything kind of stops. And so an example of this is if you have something that's balanced in physics, like something that's balanced on on a fulcrum, like a lever pulley sort of system, a lever sort of system, and it's balanced on a fulcrum, it's not moving anymore. It's not like it's oscillating back and forth like dynamic equilibrium. So in chemistry, we focus on this idea of dynamic equilibrium, and it's important that you realize that things aren't just stopping when that happens. All right. The next question here is about this collision theory of chemical reactions, and then we get into talking about activation energy and things like that in the next question. So the collision theory says that a chemical reaction, what's really happening is particles of reactants are colliding, and then they reach something that's called a transition state, and then Once the transition state is achieved, then it will fall back down and it will become the products. And so you have to kind of understand what those different things are, but I'll focus here on what makes this rate go faster. And so that transition state is sort of unstable, and so you need quite a bit of energy to get it up to the transition state. That's called the activation energy in a chemical reaction. And so in addition to a collision occurring, you need a collision that is fast enough that it has sufficient energy to reach that transition state, and then it will fall down and become the product once it has reached that sort of peak in energy. And so two ways that we can kind of increase the rates of reactions. We can have more collisions, because if you have more collisions happening, it's more likely that more of them are going to be of sufficient energy to have the reaction occur. The second thing is you could just have faster moving particles, and so each collision would have higher energy, and so it would be a greater chance that you would have that necessary amount of energy to reach the transition state. So going on down here, talking about activation energy. Activation energy is the energy you need to reach that transition state. If you don't reach that amount of energy, the reaction isn't going to take place. All right, and so going through that, the way that a catalyst helps is that a catalyst makes it so that that transition state, which is this like really awkward sort of thing where you've got atoms bonded to other atoms, but not in the way that they typically would when you created Lewis structures and things. Like things will have too many electrons, they'll have too many bonds. Hydrogen sometimes gets bonded to like two separate things, which isn't stable for it. And so you have all of this, you have this like really weird transition state. And to get up to that energy, takes quite a forceful collision. What a catalyst does, though, is it takes that really uncomfortable, weird transition state and it stabilizes it in some way. So it might go in there and lend some extra electrons or hold on to some extra electrons, or come in the middle and create a bond to something else to stabilize it, and then let that go in the end. And so a catalyst doesn't get used up, so it's not like a reactant where you put it in and it helps create the product. What a catalyst does is it kind of comes in, it helps the process out, and then it leaves. And so that's how it relates to all of these things. Okay, so on this one, we've got KEQs and Qs and interpreting them. And so here there's a really, really big thing you have to understand about KEQ and Q, and generally speaking, you just need to know what their definitions are. So KEQ is called the equilibrium constant. The equilibrium constant is a ratio between the products and reactants when it's at equilibrium. So for KEQ, it's implied that it's at equilibrium. All right, and there are some different numbers that we can get. If KEQ is a decimal, like it's smaller than 1, like 0.002 or something like that, we say it's reactant favored, because when you go products over reactants, you don't have very many products, you have lots of reactants. That ends up being a small number, okay, a decimal number. If you get KEQ equals 1, we say that that's neither product favored nor reactant favored, so equilibrium there is just lying right in the middle of the products and the reactants. For KEQ greater than 1 is product favored, so the numerator, the top of this fraction, is going to be much larger than the denominator, because we calculate this by doing the products, again, over the reactants. Now Q is an entirely different deal here. What Q is it's a test wherein we measure the concentrations of products and reactants to determine whether or not a reaction is at equilibrium. So Q is a test to see if we're at equilibrium. What we do is we compare it to the KEQ. You calculate it in exactly the same way. If we get Q less than KEQ, what this means, if it's products over reactants and our Q is too small, it's smaller than KEQ, we need more products, less reactants. That means the reaction is going to go to the right. If Q equals KEQ, that means that the reaction is going to be at equilibrium. So you perform the test and it's come back saying that, yes, that reaction is at equilibrium. If you perform the test and you get that Q is too large, that means that we need to reduce the number of products and increase the number of reactants. Again, thinking about that whole fraction, the products of reactants. And so we end up going to the left in that case. With number 7 here is asking about Le Chatelier's principle. If you want to see more in-depth conversation of this, you can look at the notes on that. But basically what Le Chatelier's principle says is equilibriums are going to react to whatever stress you put on them. If you put a stress on them, they're going to do something to undo that stress. And so if you say add one of the reactants, is going to react to that by getting rid of that reactant. Or if you remove one of the products, it's going to try and replace that product that you're removing. If you add heat, it's going to try and reduce heat. If you add pressure, it's going to try and reduce pressure. If you take away pressure, it's going to try and add more pressure. So whatever you're doing, Le Chatelier's principle says the reaction tries to compensate for that by shifting the equilibrium in such a way that it undoes whatever you're trying to do to it. So that's kind of how that works. Number 8 here, talking about Le Chatelier's principle still, it says, how is temperature affecting equilibrium for endothermic and exothermic reactions? Well, for an exothermic reaction, exothermic reactions, heat is being released, which means that the heat is kind of like a product of the reaction. So if you increase the temperature, what's going to happen is it's going to try and go to the side of the reaction with less heat. So since it's exothermic, that's to the left, okay? Because as this reaction goes in the forward direction, it releases heat, and so you're going to go to the side with less heat, so it goes to the left. All right, if you make the temperature cooler, if you decrease it, the equilibrium is going to respond by trying to increase the temperature, increase the heat, and so if it's exothermic, it's going to go to the right. Endothermic is exactly the opposite of that. And now for the calculations on this. So this first question here, it's asking about KEQ. Remember, KEQ is when we're at equilibrium, so what we're trying to do is find at equilibrium what the ratio between the products and the reactants are. So we just have to write the equilibrium expression, KEQ. Products over reactants, the coefficients become exponents. So we put the products on top. That's HI is the product there, and it is squared over the reactants, concentration of H2 and concentration of I2. Those both have coefficients of 1, and so they're not to any power. We plug the numbers in there. I get 0.30 squared over 0.40 times 0.45. Multiply those. Make sure you put them in the calculator correctly, so kind of try this on your own and see if you're getting the right answer. On the bottom, you either need to use parentheses or you say divided by twice, or maybe even if you're like super confused by the calculator, just calculate the numerator and write that, and calculate the denominator and write that, and then just do an extra step where you have a simplified numerator and a simplified denominator, and just do numerator divided by denominator in the end. That might be the best option for you. So this gives us 0.5. All right, if this is the case, then KEQ is going to be less than 1. And if KEQ is less than 1, that means it is reactant favored. On to number 10. It says consider the following equation. Again, we're calculating KEQ. This one's a little bit different though because it has a liquid in it, and liquids and solids are left out of the KEQ equation. And so in this case, actually, there's not anything on the product side at all that we're including in the equilibrium equation. So that's going to be a 1 in the numerator because there's nothing in the product side. So what we get here is KEQ equals 1 over the concentration of H2 squared, because it's got a coefficient of 2, times the concentration of O2. Plugging numbers in there, I get 1 over 0.02 squared times 10. Calculate that out, and I get 250. Right. In this case, KEQ is going to be greater than 1, which means it is reactant favored. Oh, sorry, product favored. This last one here gives us KEQ, and it asks us to calculate Q to see if the reaction is at equilibrium or not. And so Q, remember, is that test to see if we're at equilibrium. We calculate it exactly the same way as we would the KEQ. So in this case, it's concentration of CO2 squared over the concentration of CO squared times the concentration of O2. In this case, CO2 is 15 molar, so that's 15 over 0.3 squared times 2.3. Go ahead, calculate that. You should get 7,246. Now this seems like a really, really big number, but if you compare it to 1.0 times 10 to the fourth, which is really 10,000, 7,246 is actually smaller than 10,000. Okay, so in this case, Q then is less than KEQ. This means our ratio of products to reactants is too small. That means we need more products. If we need more products, then we're going to be going to the right side of this equation. So the reaction is going to proceed right. Okay, that is that. Make sure if you have any questions on this review that you come in and ask me.